So as our speaker will tell you, right around New Year's 2022 was the most destructive fire in Colorado's history here in Boulder, called the Marshall Fire, hashtag Marshall Fire. Among the people who had to evacuate were a number of CU Boulder researchers, who then turned their expertise to understanding what happens in the aftermath of an urban fire. Joost de Gouw was a leader in that effort. He's a fellow here at the Cooperative Institute for Research in Environmental Sciences, where he uses various technologies to study organic compounds and air pollutants in the atmosphere. Joost, welcome.
Well, thank you, Amber. And thank you for the opportunity to speak to you all. It's a real pleasure to be doing something very different for me. And so what I'll do is talk about the Marshall Fire that affected this area, as Amber explained, and then focus on what myself and a group of researchers did in response to the concerns about the environmental impacts that existed in our community. So this little movie is taken from the Flatiron, somewhere back here, looking out east. And it shows you how the fire started close to the mountains on the right of the screen, and then during the day it moved further towards the east into cities like Louisville and Superior. There were many things very unexpected about this fire. First of all was the date. This happened on December 30, 2021, so middle of the winter, although you wouldn't say so from the photograph. Second is where it hit. We've always sort of have a watchful eye for what happens to the west of us. There have, over the years, been many fires in the foothills behind us. And so, if anything, we would expect the fire to come from the foothills and maybe impact the city. That's not what happened. The fire started to the east of us as a grass fire, and then it moved into cities like Louisville and Superior, and that was a surprise as well. And the third aspect that's actually really unique about this fire is that it impacted a community of environmental researchers that is, among the best in the world. And so, so it impacted us personally. It impacted our friends and colleagues, and there was a need to do new research, as I'll explain to you in a minute. And of course, being in this community, there were all these tools and resources available to us to do this research. So if it happens in another community, this kind of response will not happen. But it happened here. So many of you will be from out of town, and so I wanted to show you the lay of the land a little bit. So what you see here is on the left side, the foothills. Boulder sort of in the left top of this map. And then you see the perimeter of the Marshall Fire shown here. Now, just to orient you a little bit further, we are here at the moment. This is where the fire started, so it's really only maybe 1.5 miles from here. And if you came from the airport, you likely took these roads. So it went straight through the burned area. And you may not have seen some of the impacts, but once you're aware of it, you'll definitely see a lot of construction going on along these highways. And so maybe on your way out or back to your hotel, you'll notice it if you haven't before. So what happened on this day, December 30, 2021? So it was an incredibly windy day, and I live in Boulder, and my fence blew over, and so it felt like a very damaging wind event, like we have very often in the fall. But then all of a sudden this fire started, And this photograph is taken by a colleague of mine, also from Boulder, from Wonderland Hill, which is sort of in that direction. And you can see this grass fire as it moves to the east. Again, I've indicated where we are. You can see the stadium in this photo, and Marshall Road is where this first plume started. So at 2 p.m., so now we're 2.5 hours after the fire started, it has skipped the highway, and it's now moving towards Louisville. 5:30 p.m., remember this is winter, it's dark. We can see this eerie glow from all the active fires out east. And then 9 p.m., so this is really only 9.5 hours after the fire started. The wind has died down a little bit at this point, but the fire is continuing, and there are lots and lots of buildings on fire, both in Superior, further on the right in this photo, as well as in Louisville on the left. All the lights you see in the foreground is Boulder. So this was a very destructive fire. It caused a lot of damage. The loss of life was there, but it was, given what happened on that day, very limited. Two lives were lost. Over 1,000 buildings were burned, and another 149 were damaged. So most of the lost buildings were homes. And so this is a photo taken from a drone on the day afterwards. You can still see some small fires smoldering. Another thing that's kind of striking about this photo is there are several trees that are intact. They survived this incredibly damaging fire that burned down all of the homes. The trees are still standing, some of them. And so really, what this indicates is this started as a grass fire, turned into an urban fire. What burned was buildings. It wasn't vegetation so much. It was buildings, and that is important for what gets released to the environment. And then the day after the Marshall Fire, it started to snow. So on the one hand, this was great because it put out the fire. On the other hand, it was adding insult to injury. We'd had a very warm fall, and the grasses were very dry, and they provided perfect fuel for the fire. And then literally the day after the fire, it snows, all those grasses are getting wet, and the fire danger decreased by a lot. So so what caused the Marshall Fire? I've talked about this a little bit already. But just to illustrate, this graph on the left shows the precipitation that fell in 2021 compared to the average precipitation from the 19 preceding years. So this is broken up by month. And all of the data in blue that are pointing upwards indicates that precipitation in that month was more than average. The downward sticks in red are months where the precipitation was less than average. And so what we can see is that we had a very wet spring, especially May. It was very wet. May is the growing season for grasses here. And so because of this wet spring, the grasses grew more than normal. They were very happy. But then we had this really dry fall. And all of those happy grasses dried out, and they provided fuel for wildfires. And it stayed dry well into December. The snow that fell the day after the fire was the first snow of the season, also very unusual for this area. So we had all of this very abundant fuel for wildfires. And there were plenty of grass fires started that fall. I remember driving by the foothills one day over Highway 93. It's a very windy highway, and in between Golden and Boulder, a stretch of 25 miles, I saw 3 grass fires, 3. And they were tiny, and in 2 cases there were people right there putting things out, nothing happened. But that's how easily these things get started. On December 30, we had very high winds, very high winds. And when I give a more technical talk, I go into wind speeds and all that good stuff. For this audience, I just took a photo of a Sprinter van that was blown over by the winds. That Sprinter van was parked behind the NOAA buildings, which are along Broadway. So very strong winds. On December 30, there were, again, several grass fires that started. And all but one were put out, but the third one got away from the fire department, and that turned into the Marshall Fire. So I've already shown the perimeter of the fire. So this is not everything within that perimeter burned, but a lot did. But the fire had to stop somewhere. The winds died out, it snowed, and it didn't stop because it ran out of fuel. So the photo here on the right shows you a city block from Superior that was completely destroyed, and then you see a row of new homes right next to it. And the wind direction on December 30 took the smoke from these burning homes straight towards these newer homes. And left quite an impact on them, as I'll show in a minute. So, of course, the Marshall Fire caused a lot of evacuations. Tens of thousands of people were evacuated, including, of course, the people in these homes. When they could return a few days later, of course, their happiness that their home was spared was quite quickly replaced by concern about the smoke impacts on their homes. And so here are some pictures from inside one of these homes. These were, by all means, very new and very modern homes. Despite that, smoke was blown into them and left a lot of ash and soot indoors. So the photograph on the right shows the front door, a very well-sealing front door, brand new. You see a lot of ash and soot deposited right behind it. The photo in the middle is a windowsill, a window along the staircase that goes up. This is meters away from this door, so smoke came in and billowed inside. Lots of soot on that window. The picture on the right shows another window sill, the trim along the staircase. Everything's covered in soot. So clearly people had a reason to be concerned about this. And also, what was also very upsetting was there was a very strong burn smell indoors. Your whole house smells like a campfire. So people had a lot of questions. What is this material that is in our house? What are we smelling? Is any of that toxic for us? How do we clean this up? Is it safe to return? People had all these questions. And as a result, a lot of people didn't return to these homes. Some people did, but a lot of people did not. They stayed away for weeks, sometimes months, and some people never returned because of this issue. So what did we do in response to all these community concerns? I tell you, as a scientist, when this happened, I realized, I went through this thought process, like, should we do research in the aftermath of this tragedy? And my first inclination was, I don't think so. This is a tragedy. People lost their homes. They don't need researchers running around. But then we started to get all these emails from colleagues, friends, just the general public about the impact, and we decided that a response was in fact needed. So the first thing we did was we started reading papers and reports, reports after other fires, the campfire for instance, to see what is actually known about fire impacts on homes. And we set up a website. I circled the date here at the bottom. We put this up January 4, 2022, so this is now 4 or 5 days after the fire is out. But in doing this, we found there are really many knowledge gaps. We really couldn't answer these questions that people had. So this was a useful exercise, and incidentally, this website at our research institute got an incredible amount of views. But we found that we really couldn't answer all of the questions that were out there. So we felt that we needed to do research. And so we started making measurements inside homes. People often ask, how did you convince people to put instrumentation in their homes? Well, the question was the opposite, really. How did the homeowners convince us to put our instrumentation in the home? Because we had so many people who reached out, and we kept a list of people who were interested to be involved with our study, and there were tens of homeowners and renters on there, and we couldn't help everybody. We instrumented one home in Superior, one of the homes from the photograph that I showed, with a lot of research-grade instrumentation. So what you see here in the middle, this piece of hardware, is a mass spectrometer that my group operates, and it can measure all of the gases that are indoors, the things you smell. On the right side in this photo is equipment from the Department of Engineering here on campus that measures the particulate matter, the fine particles that are in the air. And we know from previous research that fine particles are really harmful to your health. So that was a particular concern. Then we didn't just want to do measurements in one home. But we don't have 10 of these mass spectrometers. They're $500,000 each, so we have that kind of money, but not 10 times that kind of money. So what we did then is we put these small packages that you see in the lower left of the photo. We put those in a dozen other homes. So those contain a number of low-cost sensors. They're not as good as the equipment we put in this home, but they're still useful to give some idea about how widespread this issue was. And those were operated by another colleague from engineering, Mike Hannigan. We're also fortunate that the company that builds these mass specs has an office here in Boulder. They're called Toughwerk. And Toughwerk had seen all of our work on social media, etc. And in fact, they employ many of our former students and postdocs, so we know them well. And they made a smaller mass spec available that's kind of hiding there in the dark. I'll have a better picture of it later on. They made it available for our work at no cost. So this was really a group effort, a community effort to put it all together. So this is that smaller mass spec that we got from on loan from this company here in Boulder, Toughwerk. And they put it on wheels. They added 2 big batteries so you could run this thing off the grid. And we could wheel it through the streets of Superior to sniff out what the source was of the burn smells that were quite persistent, that wouldn't go away. So we smelled out burned out car wrecks, for instance. They were not the source of these smells. The fire does a really good job removing all burnable, combustible material from a car. It's just a metal wreck, literally. And then we also ran into homeowners who were concerned about their homes, so we made some measurements inside their homes. And as I like to point out, this was indeed a rocket scientist. To illustrate sort of the very high level of education in this community, this person turned out to work for Ball Aerospace. He had been a program manager on a space mission. He didn't tell us that immediately, but my colleague from Tough Work told me that the questions that guy asked were the best I've ever had about this instrument. So, and then he gave us his card, and we're like, oh, you work for Ball Aerospace. Okay, that makes sense. We also brought this mass spectrometer to people's homes in a vehicle, and then we measured their air inside their homes. We did this for roughly a dozen homes in the burned area, and then another half dozen as control homes that were in Boulder and in Longmont. So this served various purposes. You can see my colleague Abby Koss here in the photograph on the right. She's talking to homeowners. They're watching in real time as the instrument is taking data and is telling them what is in the air that's in their home. This is the ultimate outreach. So it provided an outreach opportunity. It provided valuable data for our study. Also, for these people who had been worried about this issue for weeks at this point, it was really the first time that something happened, right? A car pulls up with CU researchers, they unroll tubing, they unroll power cords, and they start measuring in your home. And I think for these people, it was very important that somebody listened, took their concerns seriously, and took data. The final thing I want to point out is when we pulled up, we would plug in to recharge our batteries. We would unroll gas lines so we could start sampling from their homes. And then we had 20 minutes to just wait for the data to come in. And so we would talk to the homeowners, all of them. And we would explain what we were doing, but we would also hear their experience on the day of the fire, and their stories were quite harrowing. And I felt that, in addition to the science, these visits had, if you want, therapeutic value for a lot of people. They finally got to tell their story, and that was important to them. So what did we find? So the first thing I want to talk about is we took samples of that ash and soot that was deposited indoors, and we analyzed it. We analyzed it for trace metals, and we analyzed it for what's called polycyclic aromatic hydrocarbons. So why these two? So metals, there are a lot of metals used in homes. So you would expect to see a lot of copper, aluminum, zinc, iron, and we saw all of that. We just didn't see it in concentrations that were much higher than what you see for dust samples that you would collect in other homes or in the general environment. Why is that? Well, first of all, soil dust has metals in it, and a lot of these minerals have metals. And also, metals have been deposited for decades in our environment. So there is an elevated level of metals in our environment as is. So that was good news. Metals were not enhanced. We saw pretty similar concentrations in the smoke-impacted homes as in the control homes. Now, the compounds on the right, polycyclic aromatic hydrocarbons, those are known to come from the burning of biomass. They're toxic, and so that explained our focus on those. Again, we saw that the concentrations were not dramatically higher in the soot and ash that we collected from these homes than in soot and ash collected from control homes, and one of these control homes is my own, so this is important to me, this is personal. But we did find that the composition, the chemical composition was different. So just like with the metals, we have PAHs in our environment. They come from diesel engines, they come from barbecues, they come from different places. But when we look at the composition of the PAHs in these samples, it was different from that. And so not dramatically higher concentrations, but a different composition. And what the health impacts of that are, that's another question. I'm less of an expert there. But overall, we felt this was not bad news, carefully worded good news. So the next question is, you have all this ash and soot on the floor, does it get resuspended? When we open and close doors and windows, when we run our heaters, air gets whirled up. And now all of this material is airborne and you could potentially breathe it in. So did that happen? And our answer was no. The levels of fine particles in these homes was actually quite low. We would qualify this as very clean air. The only time we saw it go up is when these homes were professionally cleaned. And so this is a time series from one of the homes in Superior. When there's nobody there, the measurements are just, very close to the baseline, not much going on. But then during these periods when that are marked by cleaning, there are cleaning crews in there. They run vacuum cleaners, they wipe the walls, they do a lot of stuff. And it causes the airborne dust to be quite high. These peaks on the right, they go over 100 micrograms per meter cubed. That's quite bad. That's China pollution bad. So that's an important message. When you clean one of these homes, the PM will get whirled up. You have to try and limit this as much as you can by wet cleaning, by using HEPA, vacuum cleaners. But it's also important to protect yourself when you do this, so wear a mask. And then we measured the things that you smell, the volatile, what we call volatile organic compounds, or VOCs. And so our mass spectrometers measured VOCs inside these homes every second for about 5 weeks. And we also measured it outdoors because we want to know the difference. We want to know, is what we're seeing really coming from indoor sources, or is it just blown in by the polluted air from outdoors? Well, that was a very easy question. All of these came from indoor sources. So this is the time series for one compound called benzene. That's a carcinogenic. It's a big concern for health reasons. And what we do during these few hours, we switch our inlet from measuring inside versus measuring outside, back to inside to outside. And every time we measure indoor air, the concentration shoots up. We measure outdoor air, the concentration shoots down. So this is coming from indoor sources. So this is the time series for one compound. With these very sensitive instruments, we detected hundreds of compounds, easily over 500, maybe closer to 1,000. So they were enhanced shortly after we started the study, and the first data were sort of obtained 10 days after the study. But then over the course of our study, the indoor concentrations declined quite steadily for all of these compounds, actually. And so what is shown in this graph is the average daily concentration indoors versus the average daily concentration outdoors. And you see that after 6 weeks or so, this decline in the indoor concentration slows, and it becomes a value that is more typically seen inside homes. So benzene is known to be enhanced indoors. There are many products that have it in it. Also, if you have a car parked in your garage, it can be a source of it. So we wouldn't expect it to go to zero. We would like it to go to zero because it's a carcinogenic, and we would prefer to live in homes that don't have it. But it's in our environment, it's slightly elevated in homes, and that's where we got after 5 to 6 weeks with these measurements. This decrease took much longer than expected. If I had to guess before this study how long a compound like benzene would linger inside a smoke-impacted homes, I would have told you a few hours. But instead it turned out to be days to weeks, and that was a surprise. And we're still trying to understand why it took so long. A lot of people asked us, how do we clean our indoor air? Are there things we can do to protect ourselves? And so what we did was we put these do-it-yourself air cleaners together. They consist of a box fan that costs $20. You build a cube out of 4 pleated air filters. And you can build an air cleaner that costs maybe $80 or so that has a very high capacity. In this case, because we're not so much worried about the fine particles in the air, but we're worried about the VOCs, the things you smell, we used filters that have an activated carbon coating on them. And we found that they're incredibly effective. So on the right is the time series of indoor air, outdoor air that we obtained before we used one of these cleaners, during the use of one of these cleaners, and then afterwards. So what you see is as soon as we turn these cleaners on, and we had 2 of them in the whole house, the concentrations start to drop. And then after an hour or so, the air inside is now as clean as outside air. You know, that's a relative statement. Outside air is definitely also polluted in the city, but it came down to that level, and you would not expect that it can go much lower, in fact. So it took about an hour, and you see a very precipitous drop in these indoor VOC concentrations. The surprise is when you turn the cleaner off, it doesn't have a lasting benefit. You turn the cleaner off, and the concentration shoots back up to pretty much where it was before you started the cleaner. In this particular example, it looks like it's a little lower, but we've done this dozens of times, and it pretty much rebounds to the level where it was. So that's not good. We would like this effect to be permanent. On the one hand, it's still very useful, right? If you want to sleep in one of these homes, you don't feel quite secure, you can run one of these things, it will protect you, and you can now rest more assured. That's great. Scientifically, it's incredibly interesting that these levels would rebound after you turn off the cleaners. It means that there are reservoirs of these compounds inside the home, and when you take the cleaner away, these reservoirs are still off-gassing VOCs to the environment, and the concentrations build back up. We don't know what these reservoirs are. I wish we did, because then we could remove those or clean those, and then we get permanently rid of the problem. And then another topic is, as I told you before, what burned during the Marshall Fire wasn't so much vegetation. It was mostly buildings, mostly homes. And so homes contain a lot of man-made materials. There is plastic siding, there are carpets, there's asphalt, roofing material. There are cars parked in front of it, there's trash, there's furniture, there's electronics, there's all these things. And so what happens when you burn that kind of material? And in fact, the scientific literature is incredibly limited on that issue. And this was a reason for concern for the people who were affected. You know, a lot of people were pointing at their neighbors and said, well, there was an electric vehicle parked there. The battery is completely gone. Where is that material? These are very legitimate questions, right? So to fill this void, I teamed up with some colleagues for a study at Colorado State University this past summer, where we burned a lot of man-made materials in the lab, and we measured the pollutants that are released from these materials. So the photo on the left shows you a small hood. There's a flame in the middle. This is where we could combust very small amounts of different building materials. The hood sucks up the smoke, and we would sample from the duct to see what's in the smoke. And so the mass spectrum on the right is obtained with one of our instruments. It's the same one we used after the fire in Superior. And what it shows is what happens when you burn electric wire. There's a lot of electric wire in homes. So in this case, we're mostly worried about the jacket of the wire. In this case, that consisted of nylon. Nylon is a polymer. And what did we see in our mass spectra? It was the monomer, the building blocks of the polymer. And, you know, in hindsight, that was completely predictable. But it's still good to have the data to show this. And if you look harder, we also see dimers, 2 building blocks, trimers, 3 building blocks, and so forth. Now, this is incredibly useful data because what it allows us to do is go back to data from the Marshall Fire and see if some of these compounds were in fact present inside these smoke-impacted homes. And we have data for electric wire, carpets, furniture, you know, and the list goes on and on and on. So this will be very useful for us to help analyze these data. And then I wanted to close with a few remarks that are not so much related to the science, but about the nature of doing this type of work. How do you do research after a tragedy? I already told you that I was at first reluctant to jump into this project, but then we found that there simply was a need for this, and it's been very rewarding, in fact, to do this work and to hear from so many people how our work helped them, how they appreciated our work, and that's been incredibly rewarding. I've been involved with many air pollution studies. I've measured in Los Angeles, in Houston, in places that are pretty polluted. I've never had a concerned citizen call me and say, "What did you find? You know, what's in the air that I'm breathing?" And here it happened all the time. So there really was a need for this information. But it also brings up some particular issues that I wanted to close with. So there was a lot of media attention during our study. So this is me doing a TV interview in front of the house in Superior. You can see the city block that was destroyed in the back. And so how do you balance the results that are basically incoming as I give this interview? How do you balance talking about that and you know, staying within the science as we know it, how do you balance that with the need for information that's out there? That's an incredibly difficult thing to do. I don't think I have the best answers for that question, but basically at any point you do talk about the things that are true without any doubt. And the things where we're still sort of on the fence, you don't talk about them. But it's difficult because you know there's this need for information out there, and you would like to talk more, and you would like to give people assurances, but you also don't want to assure them if it's not based on good data. So that's a balancing act that was very difficult. The other thing that was interesting about these media contacts is after the interview was done and the camera was switched off, I would always ask these crews where they were on the day of the fire. And most of these crews had reported on that day. And so where most people in the area, homeowners were evacuated, so they went away as fast as they could. The first responders, of course, went towards the fire, but were incredibly busy fighting the fire. And then there were all these TV crews that went towards the fire and had front row seats to what happened. So talking to them was always interesting because they knew firsthand what happened on the day. And so I remember one of them telling us, well, we could always tell if there was a home starting to burn because the smells would change. From a campfire, it changed into a chemical fire, and that's something that had stuck with them. And that's, for us as scientists, was very relevant. The other thing is, this was, of course, a very tragic situation. Scientists are humans too, so this affects us. And despite that, you're doing research, you're doing a job, but it's hard to keep those two separate, right? And so to illustrate, this is a photograph. These are both photographs I took. The one on the left, I don't know if you can read it all the way from the back, but it's incredibly sad, yet hopeful. The photograph on the right shows you a tub of dog food that sat out in this neighborhood. So a lot of pets were lost. A lot of pets ran off, and they put pet food out to see if one of them would come back. And this was several weeks after the fire. So just incredibly sad stories, and somehow you have to keep doing your work. That's not easy. And unfortunately, with some of the science you're hearing about at this meeting, the lines between that they're pretty blurred, right? If you're working on COVID or climate change or the Ohio train derailment, you're researching issues that really affect people, and it's not always easy. And then finally, we did get several awards for this work. And so we received an award from the Boulder County Public Health Agency, and also from the state of Colorado, from the Colorado Governor's Award for High Impact Research. And so how do you again, balance your feeling when you get one of these awards where, yes, you're happy that your work was appreciated. On the other hand, this is a tragedy, and you don't want to celebrate based on that. So this photo is of our research team. It's taken in Louisville. It is now a year or so, a little bit less than a year after the fire. You can see some of the rebuilding going on in the background. And as we were getting photographed, and this was a photograph that was made, that was shown at the reception for the award reception for the Colorado Governor's Awards, we told each other, don't look happy, right? Don't look too happy. And so we all have this sort of surly expression on our faces. And yeah, how do you celebrate an award for studying a tragedy? So that's my last slide. I didn't do this work by myself. This is part of the team that researched this. So these are students, other faculty, scientists from NOAA, and I'm super grateful to all of their contributions and to you for your attention.
Who's running this on? There we go. I have a technical question. You said when you had built this box fan and you showed the decrease in the pH, you said when we took it away, it went up. Did you actually take it away or turn it off because you've concentrated it at the filter surface, and how much was adsorbed, and could that be a source and an artifact in this sort of thing?
Yeah. Yeah, it's a good question. We did just turn it off. We didn't remove it. What this activated carbon material does, it does soak up the VOCs. We use this a lot in our research to generate clean air, and so we don't expect that it will release this VOCs later. It is permanent, and they can, at some point, they stop working because all of the active sites are now full, and you have to refresh the material. Yeah, it's a good question.
Hi, wonderful talk, loved it. I'm wondering, I know the study of microbes and fungal spores and things, living things in wildfire smoke is going up. Did you look at any of that? And if so, what did you find? And if not, do you think that's a particularly pertinent question to ask because of the environment it was burning, or maybe not?
It's a good question. My team did not address this. Noah Fearer is, as you know, a professor here on campus who studies microbes in the environment. He got involved with a study of his own where they asked people to send in samples that they would analyze for metals, and I assume they're also analyzing it for microbes because that's what he does. I haven't seen any results of that. So it's a very good question. It's an interesting question, but I really don't have an answer for it. Sorry.
Hi, my name is Jessica Mazzaros. I'm a public radio reporter out of Florida covering climate change. Fascinating talk. Thank you for that. Curious how, if your data can translate into public health studies, or if it's being translated into public health studies. So like you've described what's in the air, what was in the air, and then I'm curious, how does that affect people? Thanks.
Yeah, very good question. So for each of the pollutants that we measured, you can translate that into a potential health implication. Now, we would expect the highest effects to come from air toxics, the gas phase compounds that were measured with our mass spectrometer, simply because they were really enhanced, and some of them are carcinogenic. Now, the response functions for those compounds they're incredibly uncertain. It's a really difficult question how a certain concentration translates into a cancer risk, for instance. I mean, we can give you numbers, but then those numbers are easily uncertain by a factor of 2 or 3. But yes, that's something we can and will do. This is where our data really needs to be, unassailable, right? Another thing that we did do that relates to health is one of our collaborators did surveys in the community on both on actual health effects, so people have been reporting headaches and nosebleeds and that sort of thing, and also the perceptions. Did they feel protected, you know, a week, a month, a year after the fire? Those types of questions. So we also have a lot of data coming from the surveys. Yeah.
Hi, I also have a question about that reservoir effect that you saw. So you mentioned benzenes are elevated in homes baseline. Do you see a similar reservoir effect in those homes, or is this unique to homes that have been affected by the fire?
I think the short question is we don't really know. It's interesting. My group's been researching indoor air for the last decade or so. We started out by being air pollution researchers outside. We got into this indoor air research about a decade ago. And before this project, my student was actually working on releasing things like personal care products, cleaning products indoors, and then measuring how quickly they would go away. We were trying to do this, right? But then in a gentle way that doesn't upset anyone, because who would mind if you release a little bit of perfume or deodorant inside a room? So, and the experiment turned out to be pretty difficult because things went away very quickly. And based on that, I would have expected the smoke in these homes to also go away pretty quickly. That's not what happened. So I think what has something to do with it is how much you release. In these experiments we were doing with perfume, etc., we released, you know, a tiny little bit into the air. And here there's massive amounts. And also I think with the smoke penetrated really into walls. There were people who pulled out insulation, for instance, and it was black. And I think there are just a lot more nooks and crannies in a home where these chemicals can hide out, and that takes a long time to off-gas. So does that answer your question?
Yeah, I think so.
Hi, my name is Julianne Hodges. I used to report for in Bastrop County, Texas, where wildfire is a really big thing as well. And I kind of wanted to compare like the two communities. There's a lot of like concern about future fires as well. Have you gotten any sense of the community being concerned about something like this happening again?
Yeah, of course. So this community was and is incredibly on edge because of what happened. So it's only 3 months after the Marshall Fire, there was another fire, a grass fire on the Encar Mesa. And it was much smaller. They got it under control in half a day. But the city did evacuate something to the tune of 30,000 people, including myself. And so I think part of the response was that it was because of people are on edge. So definitely there is a lot of concern. Now, in terms of the wildfire effects on the environment in the aftermath, right? What kind of chemicals are left behind by a fire? I mean, the example to point to is, of course, Maui. And I think that was a different situation because there was so much loss of human life. And that is just, you know, a next level tragedy for people, right? And so, but I have had calls from local authorities, people's reporters about the same issue on Maui. So, and I think as time progresses, it will probably increase. Yeah.
Hi, my name is Erin. I've recently moved into a drafty old house. Do you think that you would see different data if these houses were 100 years old as opposed to maybe 10 years old?
Yeah, it's a good question. Well, I would say that the drafty old house had a lower chance to survive the fire in the first place. You know, the homes where we measured, they were right downwind from these fires. They had a lot of embers, you know, thrown at their siding. You could see in the front and backyard, you could see all these bombs these fire bombs in the grass. So where an ember has fallen down, it's burned a little bit of the grass. So these homes are built to a higher standard and they survived, and that's a good news. And I'm not a building scientist, but I'm sure that they've learned a lot from this event, and I hope they've learned a lot from this event. So now if your 100-year-old home had survived, ventilation helps, but it also would have meant that you had ingested more smoke to begin with. So how the two balance out, I don't know. In our survey, where we went along different homes, we did have a range in the age of homes. We did have a range in how they were treated after the fire. And there wasn't an obvious advantage or disadvantage of living in a newer home. So,
thank you.
Hi, I'm Michelle Ramaposa. I work for the Union of Concerned Scientists, and I write about climate change, and a lot of the work that we do relates to how climate change is increasing wildfire activity. I have a couple of questions. One is more technical about your study. Were the homes that you looked at, I know you mentioned you had like a range of different types of homes that you studied. Were the homes that you looked at professionally cleaned already when you studied them, or had they not been yet? And did they all have the level of damage that nobody could live in the house during that time? Or, you know, I'm just curious.
Yeah, very good question. So a lot of homes were professionally cleaned, but it took weeks, if not months, because there was such a demand and there are only a handful of crews out there doing this kind of work. So most of our work was done before professionally cleaning, but we also have some data that were obtained during and after professionally cleaning. So what did we learn? So what these crews do very well is they remove the ash and soot, and that's incredibly helpful, I think. They wipe down all of the surfaces. They use HEPA vacuum cleaners to pull it up from as many places you can reach. In some cases, they renewed the insulation. They clean your ducts. It's all very useful work, I think. They also try to clean your indoor air with what they called hydroxyl generators. So these are sort of like our indoor air cleaner, but they're not passive. They're active. They're making radicals, and the radicals are supposed to eat up pollutants in your air. And that we found is actually very misguided. A, it doesn't work, and B, if you think about it, it doesn't make any sense. So I didn't show that data here, but yeah, there can be industry practices that are not supported by solid science like that. So that's something we definitely learned.
So the houses that smelled clean still had high levels of particulate matter and benzene?
No, the particulate matter was always quite low. But the VOC level, that's what you smell, remained elevated for weeks. And that was pretty much true regardless of the professional cleaning. In that sense, the professional cleaning didn't help. Only time really helped. With time, things got better. and then you could have the temporary relief of using these air filters, these air cleaners, as I showed. Let's see, I was going to say one more thing about it, but now the thought escaped me, so maybe it'll come back. Yeah.
Well, the other question I had was if you have any plans for further study, and what were your conclusions?
Yeah. So what we're very interested in is what was in these homes that we can relate back to sort of man-made fuels. So did we see any compounds in these homes that we can trace back to the burning of furniture, of carpet, of roofing materials, plastic siding, electric wiring? That connection still needs to be made. We've looked at a few cases, but this is where the science is too preliminary to even talk to you about it. So.
Hi, my name is Evelyn. I'm a freelancer. So you mentioned one of the challenges here is that the homeowners just didn't know what their air quality was because they didn't have a way to measure it. And I think we've all seen, home CO2 monitors, especially since COVID, to kind of see your risk with that. But are there, kind of affordable, easy to use, like accessible to an average consumer, like air quality monitors that people are using? If not, or like what are the challenges? What can they measure? Can't they measure? What are, is it just a lack of interest in that, or are there technical challenges to making those available?
No, the interest was super high in anything that said air quality sensor on it, right? People would just use anything they could get their hands on. I would say scientifically, the PM 2.5 sensors that are out there are good. They give you important information. For this particular issue, the indoor air quality, we found that the PM 2.5 was quite low, and so that wasn't the biggest concern. Now, the things that you smelled, so those are the VOCs. Low-cost sensors for those they're out there. I don't know what they do. They don't always correlate with my $500,000 instrument. So. And then you enter this territory where the information that people obtain themselves can be very unhelpful. I would get calls saying, the VOC concentration in my home is through the roof. Yesterday was okay, now it's terrible, what's going on? And when people ask that, and I don't know what the sensor is even doing, then it's a tough question to answer. You don't want to tell them you should, get rid of that sensor, because I just don't think it's helpful. But it is what you're thinking at that point. So you wish there was a more a standard that people could turn to and use this one, but not that one. That would be very helpful, I think. Yeah.
I have a question kind of related to that. How good is this sensor?
Yeah, it's very good.
Comparable?
It's very good. And that was, I think, the most upsetting to people, that they could smell the impact for weeks, if not months. And even at a point where we thought, this air is starting to be pretty normal, pretty clean, you could still smell it. And that, as a scientist, is somewhat unsettling, because it makes you realize, are we measuring the right thing here? Is there something out there that it's very low level, so it's just a tiny little peak in our spectra, but our noses are very sensitive to it? I don't know. But for the general public, that was very unsettling, right? When you tell them, oh no, your air's fine, and their noses are like, but there is something here, then that message doesn't register, so.
Hi, Professor DeGao. Lovely to see you. Wonderful talk. For those here, I used to cover his work as a writer here at CU Boulder. My name is Kelsey Simpkins, and now I work in air quality policy as a SciCommer. One thing I've noticed is that there's a lot of press attention, like you experienced after some kind of devastating fire like this or other natural disaster. Obviously, a lot of coverage of the Maui fires and other things. What kind of stories, as a scientist who studies this, would you like to see when there isn't a disaster? What stories would you like to tell, or have heard in the media by science writers and journalists on a more average kind of, general basis? Thanks.
Yeah, thank you for that question, and also it's great to see you here. Well, we respond to these disasters. Right, by doing new science, but what you'd like to see is that we become more proactive, of course, and that we study better what areas are at risk and under which weather conditions. We'd like to forecast those conditions, right? Based on the climate data that I showed, maybe we should have expected this to happen. I mentioned before, I'm not a building scientist, but you hope that the building science community is taking all of the lessons from this to heart, and that fire codes will improve as a result. Same is true for building materials. Are there things out there that are just too harmful for us when they burn? There's a lot to do, yeah, and you would hope that we're not in this mode where we just put out fires, literally and figuratively, but that we also become more proactive in responding, yeah.
Hi, Beth Quill from Science News. This question is kind of related. I'm curious if what you're doing with the mass spectrometer, if that's kind of standard practice for more general indoor air quality studies related to public health inequities, concerns over gas stoves, living near factories, those kind of things.
Yeah, very good question. I'd love for this to become more standard practice, right? I think these things can be done at costs that are not, out of reach for a concerned homeowner, for an insurance company, and they would give you, research-grade information that I trust, right? It's not this air quality sensor that gives you a high reading, but it's a trustworthy instrument that tells you. I think those things can be done. Those are changes that take a lot of time and effort to push through. Yeah, but I hope we'll see today. And like you said, indoor air concerns occurred after this fire. They occurred after the Ohio train derailment. There are concerns when you use air cleaners to reduce disease transmission, for instance. There are a lot of questions out there, and I think solutions are out there that make sense, that are not super expensive, but it does take a paradigm shift to start using them.
Hi, my name is Dr. Anwar Dunbar. Right now I'm with the US EPA. You showed a figure where you guys, you scrubbed it out of the air and the concentration dipped and it went back up. That suggests that you might have talked about this, but it was being stored somewhere, and then it was revolatilizing. Can you talk about how when they clean these houses, how they clean them, and what would give rise to that effect where you're scrubbing it out and it's going back?
Yeah. So that particular data was where we used one of these do-it-yourself air filters. So they pull these VOCs out of the air, and it gets absorbed onto the activated carbon and just sits there. But like you said, there is a reservoir of these compounds, and when you turn off the filter, the concentration goes back up. So it's like the level in a bathtub, right? Your faucet is dripping, so when the bathtub is closed, water builds up. You can pull the plug and it will drain out, but when you put the plug back in, turn your cleaner off, the drip, drip, drip continues and it will fill back up again. So it's that sort of effect. The professional cleaning for air consisted of these chemical cleaners. So they make free radicals in air. The free radicals will eat at some of these trace gases. But where it's not supported by science is they don't just eat away the chemicals, they turn the chemicals into something else, right? Chemistry is A plus B gives you C plus D, and they conveniently ignore the C plus D. Also, these free radicals will mostly react with things that are very reactive to these exact radicals, and something like benzene, for instance, carcinogenic, is not very reactive to these free radicals. So that doesn't make much sense to me. And then the third thing, and that is the most serious problem actually, the way these filters were operated is during the day they would clean, the cleaning crews would clean these homes with cleaning products. And cleaning products have these compounds like limonene that smell really nice. They're added to a lot of detergents, for instance. So at the end of the day, these homes would smell very nice. They would have been filled up with super high levels of these cleaning products. And then they turned on these filters as they left for the night. And all these free radicals that the filters made only reacted with these cleaning products. And that was never the plan, right? They were supposed to react with the smoke VOCs. But any chemistry was completely overwhelmed by these cleaning products, so that also didn't make any sense. So you make products, it's much more selective as to what you remove, and in practice, these things reacted with the things you just added to the space.
Last question, real quick.
Hi, I'm Karen McNulty Welsh. I'm a science writer at Brookhaven National Laboratory, but I have a previous life writing for children, including for the kids' version of Consumer Reports magazine. And Consumers Union does amazing product testing, and I'm just putting it out there for the freelancers here that this sounds like a great story to pitch to them, that all of these products that are being put out there for people to deal with these issues should be tested scientifically, rigorously, and we should be telling people when things don't work so they don't waste their money on them.
Yep, totally agree.
Great. Well, thank you so much.